Hello, students. This is where we talk about doing math with vectors. And I went into some detail in the big long document about, if you remember from some of your classes, doing, like numbers and their associative and commutative, how you arrange them, how you can order them, how you can distribute the, distribute multipliers, or how you can do, and how you have inverses and zeros and that sort of stuff. Right. So some of these axioms that come from math, we want to have something like that for vectors, because ultimately, we're talking about real things, and we can talk about adding things. Like if I apply a force to something and you apply a force to the same thing, those forces should add in some way. And if I apply a force and you apply a force that's twice as large, there ought to be some concept of what twice as large is. If I'm talking about traveling somewhere in multiple steps, those vectors that represent each step of the travel ought to be able to add up to me traveling somewhere and it being the full vector. So we first start talking about these graphical vectors and how do we add them? How do we add these images? And the way we add them is head to tail. And you saw this a bit in your last video. The idea is that you start at the end of one of the vectors and you travel up to the arrow, and then you immediately go to the second arrow. So that means you have to rearrange things. These vectors A and B, let me turn on annotations here, and you can see the past stuff that I've done. I'm going to erase this because I don't like it. Yeah, here is some of this. Right. So we're going to draw again, and let's make the lines a little thicker. That might help. So these things might be, A might be up here, and then B might be over here. And we'll put the little arrow symbols in. All right, so they can be in different places, right? Because there's nothing special about where the vector is. What's important is the size of the vector and the direction. When I talked about this, watching the weather on the news, and they show you the wind speed, the 30-mile-an-hour winds that occur in the mountains are the same as the 30-mile-an-hour winds on the coast. The same sort of air hitting you is going to have the same effect. Now, there might be more moisture in it, but yeah, you're fundamentally the thing that we're measuring, the wind speed should be the same. If we have the same units in the same direction, you should have the same experience in multiple places. And so all that matters is the lengths of these things and the directions. But we can move them around as we'd like. Instead of having this, if we like, we can put B in here. That's B. And then we can go and set something else up and say put A in here. And then our sum is the bit here in, along here. This is the same sum. It's the same result. So we're going to not necessarily do a whole lot of this, but where it's important, I'm going to try to show that the vectors are going to follow most of the same rules that numbers do, but you have to add them according to the rules. You have to add them according to the rules for adding vectors, or you have to add them according to the, multiply them for the rules according to multiplying. All right, and of course, we're going to define some other functions on top of that. Now, we're not going to worry too much about division because that's kind of a weird concept. It involves multiplying by an inverse, and so you have to define inverses, and not everything is going to work, but a lot of it will. So what we're going to do, if I turn off, I don't have to turn off annotations, that's good. We're going to go through the different rules. One of them is addition. You've seen how to add. Now the goal is we're going to eventually get to treat these things as numbers because we understand components. All right, and we can talk about the size of components, and we can talk about adding the components up. And the goal is to have an object like a vector and add it like we would numbers or multiply with it. All right, so we have addition. Addition looks like this. We have subtraction. Now, we don't necessarily know how to subtract two vectors, but we do have a concept of when we have two numbers and we want to subtract them, we add the inverse, right? If we want to do 5 minus 3, well, we start at 5, and then that's actually a good point. We have a number line, right? We have a number line that we normally have. You have ticks on it. Right, there's our ticks. And we can put some numbers in. So this is, right here is 1, and here is 5. And are those readable? Those are unreadable. Anyway, so we have a number line, and say we want to add 5 and minus 3. All right, we want to subtract 5 and 3. So we're going to start at 5. If I can get this thing to, all right, we'll start here. So this is 5. And then when we add 3 to it, all right, there's our 3. We just go 3 to the right, and we would get to 8. So when we want to subtract 3, we're going to move to the left. We're going to add 1, 2, 3, minus 3. And so you get 5 minus 3. And I apologize for these annotations. Obviously, I don't have a nice drawing thing, but that's it. We have an idea of on a number line, or when we're talking about numbers, if we want to subtract, we add the inverse. And we have a mental model of a number line, and we say we start at 5, and we add by going to the right for positive numbers. And for negative numbers, we add by going to the left. So we have the same model in vectors. We have A and B, and we've drawn them here head to tail like we did for addition. But when we want to subtract, we want to add the opposite. We want to add the inverse. Well, the opposite of a vector means it's pointing in the opposite direction. It has the same length. It just points the other way. So here we have B. B points down and to the right. So minus B should point up and to the left. And that gives us A minus B over here. And the ordering of these things is not crucial. All right, we can take minus B first and then draw in A. And the sum would give us minus B plus A, which is A minus B. All right, and that's horrible looking, but you get the gist of it. Right, so when we subtract vectors, we take the inverse of the thing we're subtracting off, and then we add one vector to the inverse of the other. So that's how we do math. That's how we add and subtract. So one form of multiplication, there's going to be three that you learn in the physics course. And we're just going to do the first one today. It is talking about how do we talk about vectors that are in the same direction but different sizes. And so one operation we can do is we can take a vector and multiply it by a number. Right? And so here I have the vector A drawn in. Right? And it just goes along here. But we could apply it again. We do A plus A. And that would be 2A. That would be like going 2 plus 2 is 4. And so we have 2A over here. And all the number does is multiply the length. It makes it longer or shorter. And here we multiply by a third. It makes it a third of the length. And so these numbers that we're multiplying by, all they do is scale the vector. And that's why they're called scalars. They scale the number, or they scale the vector. All right. So in this case, we can take vectors and we can stretch them in the directions we want to. And that's what's happening over here when we do subtraction. When we subtract b, we're multiplying b by -1. So we're scaling it. In this case, we're scaling it to be the same size as b, but the minus sign changes the direction. So we could come over here and draw in -2a. If I turn on the annotations on this page, -2a would look like this. It'd be the same length as 2a, but it points in the opposite direction. So that's how we multiply numbers. How we multiply vectors and add vectors. Now, as we go on in the course, we will see other things. Because you could ask, how do we multiply two vectors together? And there are rules for doing that, and they tell you different things about the things the vectors represent. In a sense, you can ask, well, how perpendicular are two vectors, or how parallel are two vectors? You can have a measure of those things. And so you know your multiplication can tell you something about how parallel they are and how big they are, or how perpendicular and how big. So we'll also go on and talk about components and doing math with those. Right. I talked about this a little bit before in the previous slides. You can break a vector into two components. One will go in the x direction for us, and one will go in the y direction. And so you can break a vector into any pair of vectors that add up to it. You can pick a vector and draw one that goes off at an angle, and find a third one that adds up. But we like to pick one in the x direction and one in the y direction, and that way we know they're going to form a right triangle. And that means we can do trig. All right, so we have some vector equals its components. Now, if we want to add vectors, we can add the components. We don't have to add the original vectors. And so here, what I've drawn is we have A and B, and these are the same A and B as before. But when we add the components, we start at the beginning of A sub x, go to the end, and immediately start at A sub y and move, and then we do bx and by. We do the additions in order. And so that should give you the same result. That should also be the r that we talked about before. All right, we can do this, and because we know how big A's and B's components are, we don't have to deal with drawing this out actually. We can go in and say that A sub x might be, let me make this nice and big. A sub x might be 3, come on, why aren't you working? 3 in the x direction plus 4 in the y direction, and then we'll go and look at this and it'll be plus 3 in the x direction for B, and then we'll have plus minus 1 in the y direction. All right, so that's how I've written it out. And we'll make this nice and big if we can, and we'll stretch it out. Yeah, there we go. All right. So, all right, we could do our math like this. And the idea is that the x things here that I'm putting in, which I'll define in a minute, you only add those things. Basically, it goes through over 3 in the x direction, and then over 3 more in the x direction. So it goes over 6. And then it goes up 4 and down 1. So it goes 3 in the y direction. All right, so we have an idea of manipulating just the numbers. And the rest, you know, some of the stuff will just be bookkeeping when we get there. But that's our result. Our result just adds them up. And in the x component of the result, it's just adding these x components. We can rearrange the components. Right, so we have ax plus bx, right, ax plus bx here, and then we have ay plus by there, and so that lets us find these components, rx and ry. And this is useful because sometimes you can set the problem up where you're just dealing with numbers. You don't care about drawing this thing out like this. You don't necessarily need to position A and B and make a drawing like this. You can just find the components, do the math on it. So those components, the little x's and y's that I put in there, and you can imagine when you did your algebra, those were x variables and the y variables. Those are actually units. Right? This is like saying I drove 20 somewhere. Well, that has two different connotations. If I drove 20 miles, you know, that's not too bad. That's driving from home to school. Or I could drive 20 kilometers, which is about 5/8 as far. Or I could drive for 20 minutes. And that 20 minutes can be different whether I'm going for 20 miles an hour or 70 miles an hour. Right? So the units are important in the measurement, and they're important in the vectors. And the idea for the unit vector is we've identified these that everyone will understand what these are. That we have special arrows, special units that go only in the x direction or only in the y direction, and they are exactly 1 unit long. This could be 1 meter or 1 kilometer, or these could be velocities. It could be a meter per second or a centimeter per second. Whatever our unit is in the problem, these go one of them. So the idea is that you can look at these, and A, Y, and AX look like they're about 2.5 of these unit vectors. But they're a bookkeeping. And the trick is that we can write a vector as a number of copies of this x vector plus a number of copies of the y vector. And that makes things a little easier. If I go back to this problem, the way I laid it out, let's turn on annotations somewhere. Where did I do that? All right, here was my annotations. What we have here is if I put in a drawing here, we can put in what looks like unit vectors. So this is y hat, and this is x hat. There, notice there's little hats. I don't know if I've talked about this before. When we talk about vectors, we put a little symbol over them that says those are vectors. Right? And so when we do unit vectors, we put a little symbol over them that says these are the unit vectors. And so here we have just some numbers times these unit vectors. And I tell you, we're going to use 3 copies of the x thing, and that gives you a sub x, and then 3 copies of the y, or sorry, 4 copies of the y thing, which I'm bad at drawing. But we use multiple copies of the unit vectors to build up these components. And the reason we do that is so that we don't have to actually deal with the vectors themselves. We just deal with components in each direction. These things, a sub x and a sub y, note there's no arrow above them. Right, there's our arrow. There's no arrow on those. Those are numbers. We can write this as, let me put in, all right, 3 in the x direction plus 4 in the y direction, let's say. And they're just numbers. And we stretch it out, and you notice that it just jumps up there like that for some reason. We could express it like that, and then we could put in our hats, because they're not really variables. They're 1 in the x direction, 1 in the y direction. Now, your textbook, all right, obviously these slides are a little bit different. Your textbook also uses I hat and j hat. And if there's a z direction, you'll see z hat or k hat. So I think I do this in the other slides. I try to stick with the textbook and use IJK. So we'll try to do that as well. We'll solve problems. You'll see I and J, but you may also see X and Y, and that's perfectly fine too. They're just saying I hat says 1 in the X direction and J hat says 1 in the K direction. And it's a historical thing why they picked I and J and K. And it has to do with other sorts of math that people were doing. So, ultimately, we have these unit vectors, and that's the important bit, is that we can work with the unit vectors. So it's just bookkeeping, because what we want to do is work with the numbers. We want to treat these things like numbers, but we have to do the stuff in the X direction and then separately do the stuff in the Y direction. They don't mix. There is no way to take this X unit vector and make a Y unit vector out of any number of these. We can't make a sub y out of any amount of a sub x's, and vice versa. Right? We have to treat those 2 directions separately until the very end when we put them together and we get some vector that represents the magnitude of an arbitrary vector. So we have a problem that I'll talk about. We have a vector that we've stated. It's 175 meters long, and there's the angle expressed in here that is 50 degrees. And what we want to do is find these components. And here it's expressed r, and it's component x and y. That's kind of common. R vector is the displacement vector in physics. It commonly gets used for things like the radiuses, or how far something has moved, or its current displacement from an origin. And R vector will have components x vector and y vector. They're just the components of the displacement. But we'll define, when we talk about motion, we'll define what displacement is, but it's essentially as the crow flies distance. All right, it is the direct straight line distance between 2 points. So we want to find these. Well, if we look at this, we have an angle and we have a hypotenuse, right? We know what R is. We can find the other two sides of the triangle. That's trig. And so that's what we do. We sit down and say, well, this side, the y side, is the opposite side. So it ought to be, the ratio of y and r should be sine of theta. And so we apply, we have a formula we stated before for r sub y is going to be r sine theta. And that's 175 meters sine 50 degrees, and that's 134 meters. And you get that. And x is the adjacent side to this angle. And so adjacent over hypotenuse is cosine. And so when we rearrange it, we get r sub x is r cosine theta. And so we get the two lengths of that. So the vector r is 112 1 meter units in the x direction and 134 1 meter units in the y direction. This is the vector. And we can state this without drawing anything. That's why this is useful. And it's bookkeeping. There's no way to take any parts of this and make parts of this over here. They're like when you express an equation, 2x plus 3y is 7. There's no way to take the bits of x and make y out of it, except to solve the equation in some way. Right? And that's our goal. We're trying to use these components to find what we need out of them. Now, like I said, we can go backwards from that. We can take our components and find the necessary hypotenuse and angle. And this is where I'm going to stop the video so that, part 3, we will do what can we do with inverting this. How can we find distances and directions from components?